functions, graphs, and equations. In the last topic, we studied relations represented by sets and maps. In this topic, we will turn our focus to relations that are expressed as graphs and equations. First, let's recall our basic definitions. A relation is a set of ordered pairs. A function is a relation in which each x value corresponds to exactly one y value. The domain of a relation is the set of all x values in the relation. The domain is also referred to as the set of input values. The range of a relation is the set of all y values in the relation, also referred to as our output values. Hopefully, these definitions look familiar to you. Now, in the last topic, we looked at relations and functions expressed as sets and maps. In this topic, we are looking at functions and relations in both graph form and equation form. Now, when dealing with relations and functions in graph form, it is important to recognize the difference between finite and infinite relations. Let's take a look at an example. Consider the relation defined by the following set of ordered pairs: 0, 0, 1, 1, 2, 4, 3, 9, 4, 16, 5, 25. This relation is finite because it contains a finite number of ordered pairs. In this example, 6 different ordered pairs. If we wanted, we could represent this relation with a graph by plotting the individual points. The graph of this relation would look as follows. Notice our points: 0, 0, 1, 1, 2, 4, 3, 9, 4, 16, and 5, 25. The domain of our relation, recall, is the set of x values, the input values. Those would be the numbers 0, 1, 2, 3, 4, and 5. The range, recall, is our set of y values, the output values, the y coordinates of the points. This is the set 0, 1, 4, 9, 16, and 25. Is this clear from the graph? Do you see where the domain and the range come from and how they apply? Just to be clear, when you have a relation that's finite, it will graph as a set of individual ordered pairs. In other words, a finite number of points. Let's take a look at a different example. Consider the relation that's defined by the set of all y equal to x squared, such that x is any real number. This relation is infinite because it contains an infinite number of ordered pairs. The graph would look as follows. Don't worry about how to get the graph of this relation yet. We'll discuss that in a later topic. For now, what we want to observe, though, is that when you're graphing a relation that is infinite, notice it consists of an infinite number of points. And this is defined by a continuous line with arrows on the end, meaning that this will continue forever and ever and ever. The domain of this relation is the set of all x values. And notice, since x can be any real number, that means our domain consists of all the numbers from negative infinity to positive infinity. Looking on the graph, that means all of the numbers on the x-axis from the negative infinity to the positive infinity. This represents our domain. The range consists of all the y values. And what can y be? Well, if you look back at your relation again, y equals x squared, where x is any number. And if you square any number, you always get something positive. Therefore, looking at the graph, our graph is always positive in terms of y. It never falls below the x-axis. It never falls down here where y values are negative. Therefore, our range is said to be 0 to infinity. Do you see how this pertains to the graph? Let me now recap what we've just discussed. As the examples prior attempt to illustrate, finite relations will have finite domains and ranges. In this case, we can list the items in the domain and the range using set notation, and the graphs will consist of a finite number of points. However, infinite relations have much larger domains and ranges. In that case, it's usually easier to use interval notation or inequalities to express the domain and the range. Now, as we observed in the last topic, determining whether a relation is a function is pretty straightforward when the relation is represented with a set or a map. We look to see whether each x value maps or corresponds to one y value. However, with graphs and equations, it gets a little more tricky. Luckily, we have a helpful tool to apply when a relation is expressed in the form of a graph to determine if it is a function. This tool is what we refer to as the vertical line test. The vertical line test is as follows. If any vertical line hits the graph of a relation more than once, that relation is not a function. For example, on the left, notice we have a function defined by the blue curve. If we draw any vertical line, denoted by the red dotted lines, notice each of these vertical lines only hits this relation in one point, denoted by the green check marks. This means this relation here is a function. Every x will map into one y value. On the right, let's take a look at this relation, again defined by the blue curve. To perform the vertical line test, we only need to put one red dotted line, one vertical line. Notice it hits in two places on this relation, denoted by the red x's. That means this relation is not a function, for this x value 2 maps to two different y values. To recap, if your relation is expressed as a graph, to determine whether it's a function or not, you can perform the vertical line test. That is, when you draw any vertical line, if it hits the relation in more than one point, then that relation is not a function. Now let's take a look at relations and functions expressed as equations. We start with the definition. We say an equation defines y as a function of x if each x value that satisfies the equation corresponds to exactly one y value. Now, to decide whether an equation defines y as a function of x, we can apply the following principle. Solve the equation for y. If more than one solution is obtained, then y is not a function of x, since each x value would give multiple y values. Let's look at this example. The equation y squared equals x does not define y as a function of x. This is because when we solve for y, we have to apply the square root property, right? Y squared equals x, we take the square root of both sides. This leaves us with two solutions for y. Y squared equals x, after we apply the square root property, gives us y equals positive x or y equals negative x. This means there are multiple values of y that pertain to the initial value of x. And this means our original relation, y squared equals x, is not a function. Let's recap everything we've discussed thus far. Domain and range. When finding the domain or range of a finite relation, we want to list each x value or y value in a set. When finding the domain or range of an infinite relation, we want to use interval notation or inequalities to express the domain or range. Determining whether relations are functions. When given a graph, the vertical line test can be used to determine whether the relation is a function. When given an equation, we want to solve the equation for y to determine whether the relation defines y as a function of x. Let's now work several examples together to put these ideas into practice. Hopefully, it'll make everything a little more clear. Example 1. Identify the domain and range of the following relation. Write your answer using set notation and interval notation when appropriate. State whether the relation is a function. Example 1a. Notice this example consists of a graph of a finite set of points. To best identify this relation and the domain and range, I'm going to identify each point with an ordered pair. That helps me to see the x-coordinates and the y-coordinates, which we need to obtain our domain and range. So let's start by labeling each point on this graph. This first point, notice, is at -3 for x and 1 for y. So this is the point -3, 1. This point here next to it, this one is 0 for x and 1 for y. We'll label that as 0, 1. Let's do the point up here in this quadrant, the first quadrant. This is 5 for x and 4 for y. So that's the point 5 for x and 4 for y, or 5, 4. The ordered pair for this point, let's see, that would be 4 for x and -2 for y. And the last 2 points. This point here, -1 for x, -2 for y, and finally the last point here would be 0 for x, because it falls on the y-axis, and -4 for y. We have 1, 2, 3, 4, 5, 6 elements in our relation. Let's now identify the domain of this relation. The domain, recall, consists of all the input values, the x-coordinates, if you like, for each of the ordered pairs. Let's look. Our x-coordinates, I will underline, are -3, -1, 0, notice 0's here too, 5, and 4. So let's write those numbers down in our domain. The domain consists of -3, -1, 0, 4, and 5. Next, let's look at the range. The range is the set of output values of this relation, the y values, if you like, the y-coordinates for each ordered pair. And the range then would consist of the objects that I'm underlining here. That would be a 1 here, a 4 here, -2, -4, and a -2. So let's list those as a set. The range, starting at the bottom and working our way up, would be -4, -2, 1, and 4. Do you see those y values that you obtained for the range? Perfect. Now, the last question. Is this relation a function? What do you think? Well, in order for the relation to be a function, every x value must map to at most one y value. Or another way to look at it is, if you have a graph, does your graph pass the vertical line test? Well, notice this relation does not pass the vertical line test. If we were to draw a vertical line right here, straight down, notice that we pass through 2 points, this point and this point. Our x value of 0 maps both to the number 1 and to the number -4. This means our relation is not a function. So, because the value 0 maps to 2 different y values, this relation is not a function. Again, because the value 0, which is in your domain, maps to more than one value in your range. Make sense? Perfect. Let's move on and look at example 1b. Example 1b. Identify the domain and the range of the relation. Write your answer using set notation and interval notation when appropriate. State whether the relation is a function. This time, notice the graph of our relation is a continuous line segment. It starts here at the point -4, -5, and continuously runs, hits every point in between up until the point 4, 5. Because it's a continuous line here, or a continuous curve, the best way to identify the domain and the range is to use an interval notation. That's because this is an infinite set of points here. So let's start by identifying the domain and the range. We start first with our domain. Recall our domain as our set of inputs, or our x values if you like. We can identify them by looking along the x-axis. Now notice this curve starts at what x value? The smallest x value that this starts at is at -4. See how this point here corresponds to -4 on the x-axis? So our domain begins at the value -4 for x. Now it's a closed dot, so we're going to write our interval notation with a closed bracket. So we're starting at -4. Now how far are we going to the right along the x-axis? How many x values are included over here? Well, let's see. This point here designates the end of our relation. And notice that corresponds to x being 4. There's no other x values that correspond to this relation any higher. So 4 is the limit on the right. That means our domain consists of all the numbers from -4 to +4 along the x-axis. Do you see that? Let's now consider the range. The range, recall, is your set of y values, your outputs. When we look at the range pertaining to a relation as a graph, then we will look along the y-axis and say what's the smallest y value and largest y value that pertains to this relation. So let's look at the smallest y value first. Again, take and consider this point here, which ends the relation, and bring it over and notice that it corresponds to -5 on the y-axis. That's the lowest that this graph goes. It doesn't go any lower. So our range starts at -5 on the y-axis. It then continues all the way up and goes all the way up until what number? Well, the highest value, y value, that would pertain to this relation would be the y value that pertains to this end point here. And that is at 5 positive on the y-axis. We don't go any higher. So the range, we would say, goes from -5 all the way up to +5. Now, is this relation a function? Does this relation pass the vertical line test? Well, if we were to draw a vertical line anywhere along this relation, along this graph, notice that any vertical line we draw only hits the point, or excuse me, only hits the relation in one point. No more. Any vertical line you draw will only hit this graph in one point. That means this relation is in fact a function. So the relation is a function. That's because it passes the vertical line test. In other words, every x maps to only one y value. Cool, let's move on now and let's look at our next example. Before we go on and work more examples together, I want to quickly discuss some different notations that we can use to write infinite sets. In the last example, we used interval notation to denote sets of infinite points. We wrote both our domain and range as intervals. Well, you can also look at an infinite set of points on the number line as a graph, or using set notation. Let me show you a comparison of these different types of notations. Let me start by categorizing these notations into 3 types: interval notation, graph on a number line, and set notation. Let's now consider a specific set of infinite points. Let's consider the interval of all numbers from -4 to +4. This would be the interval notation for that set. If we were to express this same set on the number line, we would graph and shade all the points that are in between -4 and +4, including, and that's why I'm darkening in those endpoints, including the values -4 and 4. Another way to interpret this would be in the following set notation. This is all values x that fall in the real numbers in between -4 and +4, which we write as all the values -4 less than or equal to x less than or equal to 4. All the values in between -4 and +4. Let's look at a different infinite set. Suppose I have the set 0, infinity. The interval notation would look like 0, infinity with open brackets at each end, meaning that we're not including those endpoints. If we graphed this on the number line, we would start at 0 and have an open circle because we don't want to include that value, but we want to include all the numbers that are bigger than 0, everything that falls to the right. In set notation, this would be all the real numbers, such that, and we could write x is greater than 0, all the numbers that fall to the right of 0. Let's look at another example. Suppose I wanted the numbers from -3 to +8, where -3 is closed and +8 is open. The graph on the number line would look like this. We would be shading all the values in between -3 and 8, where -3 is included, denoted by a closed dot, and 8 is not, denoted by an open dot. The corresponding set notation would be all elements of the real numbers, such that -3 is less than or equal to x is less than 8. And finally, suppose you encounter the infinite set of all real numbers, all the numbers on the number line. The interval notation would be -infinity to +infinity. If we were to graph it, it would simply be all the numbers on the number line, so we'd shade the entire number line to designate all the points on it. And the set notation, well, you could simply write the symbol R, which stands for all real numbers, or you could write a set. X is an element of all the real numbers. Sometimes you might even see it written as x is an element of real numbers, x is an element of the real numbers such that -infinity is less than x is less than infinity. There's lots of different ways to denote this set. Anyways, the reason I point out these different notations is that as you're doing your homework, you might be asked to give an interval notation, you might be asked to graph on a number line, or you might be asked to express your answer in set notation or inequality notation. All these different ways represent infinite sets. Let's move on now and take a look at more examples.